This research paper explores the accuracy of human inference making from visualizations, comparing it to Bayesian agents under varying uncertainty and sample conditions. The study challenges the assumption that a rational agent is always ideal, instead examining scenarios where human visual inferences might outperform those of an ideal Bayesian agent. In 2 experiments, participants made visual inferences from bivariate visualizations on various topics, externalizing their prior and posterior beliefs using a graphical elicitation device. Results show that participants were more accurate in inferring the true correlation level than both informed and uninformed Bayesian models when the visualization showed extreme samples. This advantage was particularly pronounced with icon arrays and in situations where there was a higher consensus around the ground truth. However, participants were less precise in estimating the true uncertainty of the data generating process, often displaying unwarranted confidence. The study reveals that individuals frequently diverge from normative inference when interpreting visualizations, but these deviations proved advantageous, particularly when examining extreme datasets and small samples. The findings highlight the potential for integrating human and machine inference in visualization tools, providing guidance on how to interweave the 2 capabilities. The results suggest an alternative design strategy that seeks to harness human heuristics in visual analytics, rather than entirely aligning analyst behaviors with rational frameworks. The paper also discusses the implications of heuristic versus rational decision-making, highlighting that non-rational thinking could prove beneficial in visual analytics, especially when faced with improbable data. The authors emphasize the importance of understanding how human and machine inference making can complement each other, rather than seeking to align analyst performance with normative, statistical inference. Overall, the study contributes to the development of more intelligent visual analytics systems that adaptively encourage analysts to leverage their intuition and trust their gut, or provide computational assistance when users are more prone to biased inference making. In a recent study, researchers investigated how humans and statistical agents, specifically Bayesian and flat prior agents, interpret and infer relationships from data visualization. The experiment involved participants viewing scatterplots, bar charts, or icon arrays representing a hypothetical relationship between family income and BMI among U.S. children. Participants were asked to predict the relationship before and after observing the sample data, and their perceived sample reliability was also recorded. The results showed that the flat prior agent exhibited the smallest distance to the real slope, followed by the informed Bayesian and then participants. Participants demonstrated higher variability in their ability to infer the true slope, particularly when using icon arrays. This suggests that humans are less accurate and more variable in their inferences compared to statistical agents. In terms of resilience to spurious samples, participants were less influenced by extreme samples than both informed and uninformed Bayesian agents. Icon arrays afforded the highest resiliency, followed by scatterplots and bar charts. Consensus around the ground truth and sample size also played a role in enhancing resiliency, with participants least influenced by small samples. Comparing human versus machine resilience, the study found that humans outperformed statistical machines when samples were consistent with the ground truth, but underperformed when samples were less consistent. This highlights the importance of understanding how different visualization types, consensus levels, and sample sizes affect human and machine inference accuracy and resilience. The research further explores the inference abilities of human participants and statistical agents in various scenarios, focusing on the impact of social consensus and uncertainty in the data generating process. It begins by analyzing the sensitivity of human and Bayesian agents to extreme samples, showing that humans exhibit better resilience to spurious samples, especially in high consensus topics. The study also examines how participants characterize uncertainty, revealing overconfidence compared to Bayesian agents. In Experiment 2, the researchers investigate whether social information can compensate for statistical uncertainty, finding no interaction between these factors and no decrease in the performance gap between humans and Bayesian agents with increased uncertainty. The results suggest that humans benefit from social consensus and reduced uncertainty separately, without an interaction between these factors. This implies that social information does not aid in reducing statistical uncertainties. The study concludes that human and statistical inference excel in different scenarios, highlighting the importance of understanding these differences for improved decision-making. This study explores human inference making from visualizations, comparing the accuracy of human judgments with those of Bayesian agents. The central hypothesis is that while humans exhibit non-rational tendencies, they may possess advantages in certain scenarios. Experiment findings support this notion, showing that although participants were generally less optimal than Bayesian benchmarks, they surpassed machines in specific instances and were better at discerning and disregarding spurious datasets. However, the results also indicate that humans exhibit higher variability and consistently exhibit overconfidence. The research suggests potential for collaboration between humans and statistical or AI-based agents for inference making, enabling each to complement the other's limitations. This collaboration could take the form of delegation, where each agent takes responsibility for certain inferential tasks depending on the sample size and quality of human intuition. The findings challenge the assumption that normative rationality is always ideal and show that analyst gut reactions could provide an advantage in certain visual analytic contexts. The study's results have implications for the design of visual analytics systems, suggesting that these systems should retain a role for analyst intuition, even when their conclusions may seem biased. Limitations include the use of varying sample sizes, the involvement of crowdsourced participants, and the controlled workflow in the experiments. Future studies should attempt to replicate the findings with practicing data scientists under more realistic tool usage conditions. The paper also discusses Bayesian-assisted inference from visualized data, focusing on how Bayesian cognition can improve data visualization. It presents various studies and findings on how people make decisions under uncertainty, including biases and heuristics. The authors emphasize the importance of understanding these biases to improve data analysis and decision-making. They also highlight the role of AI in enhancing human decision-making capabilities, particularly in data-intensive tasks. The paper explores different methodologies, such as conditional delegation, to promote truth over publishability in scientific research. It concludes by emphasizing the need for a more nuanced understanding of human-AI collaboration and its implications for data science and decision-making.